Okay, so let's just start with a standard uh, flat problem. Let's take a ball on flat ground and let's shoot it up in the air with an initial velocity of 15 meters per second at an angle theta of 20 degrees. Now, if you're comfortable with this problem already, we've done one of these in class, then go ahead and just skip this video and go on to the next one. Otherwise, what's going to happen with this problem? This problem, the ball is going to go up in the air and come back down and land somewhere here. And we can look at this and we can ask a bunch of questions. We can ask, how high does this go? We can ask, how far does it go? We can ask total time in air. So we can say, how much time does it spend up in the air? And we can also ask, what's the final velocity? So these are all good questions to ask, all straightforward given those initial conditions. We know that we need a x and y column, so v0, v, a, t, delta x, something for the x direction, something for the y direction. And since we have an x and a y column, I know that I'm going to need an xy coordinate system, x and y, just a regular coordinate system. And I immediately noticed that my v0, 15 meters per second, is not in the x or the y coordinate system. It's at some funny angle. So I need to break that up. So I'm going to go over here and say, drop bigger, if my v0 is 15 meters per second, I'm going to break that up into two components. I'm going to break it up into a v0 in the x direction and a v0 in the y direction. And what happens is v0 in x and v0 y, we know that the angle here is 20 degrees. So I could use my favorite trig function. I know that the sine of 20 degrees is opposite over hypotenuse. So I know that sine 20 is equal to v0y over 15 meters per second, or v0y is equal to 15 sine 20 meters per second. And if I plug that into my calculator, 15 sine 20, and since 20 is degrees, I want to make sure that my calculator is in degree mode. V0y is 5.13 meters per second. I can do the same thing. V0x is cosine, so cosine of 20 degrees is adjacent V0x over 15 meters per second, which means that V0x is 15 times the cosine of 20 degrees in meters per second, or 15 cosine 20 is going to be 14.1 meters per second. So I now have my two V0x and V0y that I can put over into my column of variables over here. V0x 14.1 meters per second, V0y 5.13 meters per second, and those are my initial conditions. I don't use the 15 or the 20 anywhere. Okay, we also get for free the acceleration of 0 and 9.8 meters per second squared in the y direction, and the 9.8 is down. So now we have to decide, what do we want to do? Well, let's just answer that first question. First question says, how high does the ball go? So I'm interested in this height right here, delta y. And I know something special about that point. Right up here, the velocity in the y direction is 0. At that point, the velocity is purely horizontal. So I could say, if I want to find between the beginning and that top point, I'll make that top point the final point. So I can say that my velocity in y is 0 meters per second there. And as soon as I do that, I'm going to label this column. This is to the top of the problem. That means that if I calculate the time, it's going to be the time to the top, and if I calculate the delta y, it's going to be the delta y to the top. Once I do that, I can very easily just use my equations. Delta y is equal to v0t plus, I don't know that one. Delta y equals v0t plus 1/2 at squared. Actually, notice I don't know t, so that's going to solve for t, but that's not going to, and delta y I don't know, so I can't actually use that equation. Let's use v squared equals v0 squared plus 2a delta y. That actually will give me my delta y, and I know everything else. So delta y is equal to v squared minus v0 squared all over 2a, or it's equal to 0 squared minus 5.13 meters per second squared all over 2 times negative 9.8 meters per second squared. So I end up with 5.13 squared divided by 2 and divided by 9.8, and I get a delta y of 1.34 meters. So that is going to be 1.34 meters. That is going to be my how high. I'll just put 1.34 meters right up there just so I know what's going on. Okay. Notice that I chose a point here at the top, so everything in that column is the top. If I calculated the time, I could now use this first equation to calculate the time. I could share that time and figure out the distance. That would give me the distance halfway, but I'm not actually interested in that anywhere. Okay, so now what's the next question? The next question is how far does it go? How far does it go and total time in the air? Those are both questions that are interested in this point right here. I want to know clear to the end over here what's going on. All right, so I'm going to need another column of variables to the end, not just to the top, but I want to go clear to the end. So my initial velocity is still the same, 5.13 meters per second, and my acceleration is still the same, 9.8 meters per second squared down. But what's different is my velocity in the y direction is not 0 here. It's not 0 right here, so I can't use this velocity. What I do know is that between the beginning and the end, I'm at the same height because I'm a flat surface, so I end up with a delta y of 0. Now that I know those three things, I can use delta y equals v0t plus 1/2 at squared to find the time. So that means 0 is equal to 5.13 meters per second times time plus 1/2 times negative 9.8 meters per second squared times t squared. Or 0 equals 5.13t minus 4.9t squared. I can solve that equation, factor out a t, and solve. So 0 equals t times 5.13 minus 4.9t. And then solve that, and I end up with t equals 0, and t equals 5.13 divided by 4.9, 1.05 seconds. And both of those answers are real. When does the ball get to a height of 0? Well, it gets to a height of 0 at the beginning and at the end. So we know that the 1.05 seconds is how much time it takes to get to the end. So we notice 1.05 seconds. 1.05 seconds is the time to the end. That's actually my total time in the air, 1.05 seconds. Okay? So I answered that one. I didn't even know I was answered it. How far does it go? We now have to share that time, 1.05 seconds, with the x so I can figure out the distance. Then I can say, oh, delta x is equal to v0t plus 1/2 at squared. But in the x direction, what do I notice? I notice that the acceleration is 0, so this whole term goes away, and I end up with delta x equals 14.1 meters per second times 1.05 seconds, or 14.1 times 1.05 is 14.8 meters. So I end up with a 14.8 meter distance is the how far. Now, final velocity. Final velocity, we are talking about this position right here. So I want to know the x velocity and the y velocity right here. So for final velocity, Final velocity in x actually is pretty easy. We know the acceleration is 0, so we automatically know the final velocity in x is 14.1 meters per second. So v in x is equal to 14.1 meters per second. The final velocity in y we can just calculate. Velocity in y is equal to v0 in y. V equals v0 plus a t. So v in y is going to equal to 5.13 meters per second minus 9.8 meters per second squared times time, which is still 1.05 seconds, and we end up with 9.8 times 1.05, and then we get 10.29, and we have 5.3 minus 10.29, 5.13, sorry, and we end up with Vy is equal to negative 5.16 meters per second. So we have two values for velocity, Vx 14.1 meters per second, Vy is 5.16 meters per second in the negative direction. If I want to put those together and say what is the actual vector form of the velocity, I just have to do the backwards form of what we did up here. Here we took a velocity in an angle and put it into components. Here I know the components. So I know that Vx is equal to 14.1 meters per second. I know that Vy is negative 5.16, so it goes down 5. Vy is equal to 5.16 meters per second. And so then I can easily take my hypotenuse here and say the hypotenuse is just using Pythagorean theorem because I know that that's a right angle. So 14.1 plus squared plus 5.16 squared, and then square root the answer, and I get an answer of 15 meters per second. And I also have to figure out this angle, and in this case I'm just going to use my favorite trig function. I know that the tangent of theta is opposite over adjacent, so it's going to be 5.16 over 14.1, or 5.16 divided by 14.1, 0.3659. So the angle is going to be the inverse tangent of 0.3659. So I'm going to say inverse tangent, and I end up with an angle of 20 degrees. And 20 degrees, how is that different than this 20 degrees? Well, based on my picture, this 20 degrees at the beginning was 20 degrees above the horizontal. This 20 degrees here is 20 degrees below the horizontal. So I might say that just to be explicit, below the horizontal or below the ground level. So initial velocity or final velocity would then be 15 meters per second, 20 degrees below the horizontal. So I'll just write that up here. 15 meters per second, 20 degrees below horizontal. And I now have, for your viewing pleasure, the answers to all your questions. So that's a straightforward problem, answered all the possible questions given those initial conditions.